Hello, this is Jack Jackson. In this playlist, we're going to be looking at transformations. Um, so now, first of all, for my class, this transformations chapter has as embedded exercises as we work through the notes. Most of these are pretty straightforward. I give you an example of how to do something and then ask you to do it immediately after. So when you're watching these videos, we're going to be doing the same thing. I will show you an example and then I'll immediately give you another problem and ask you to work that problem on your own. I will not provide the solution to the second problem. I will provide you a solution to the example right before it. We're going to show you how to use Geometry Sketchpad and GeoGebra to perform some of the constructions, both using the built-in shortcuts for doing these, the tools, but then also how to use maybe the compass and straight edge kind of tools, how to do those by hand. So we're going to do some physical constructions with the pencil compass, straight edge ruler, and or protractor. Um, Um, you can use a pro-radian protractors for radians or standard protractors with degrees, compasses and rulers. You may have some in the classrooms, you may have some where you are, or you can buy some relatively cheaply. Now, uh, in the case of my class, you're going to want to do those things on paper. And in my class, I want you to turn in the Word file electronically. So you want to do a photograph or a scan of that and get that graphic in there. But at home, if you're just watching these videos, just get you some paper and do these. You'll want probably just plain unlined paper for doing the constructions. We'll also use some patty paper. Patty paper is basically like you put between hamburger patties, and that paper is real thin so you can see through it, and so we can look through it and trace things and then use that to explore some of these ideas as well. Okay, all right, so there's going to be at least 59 exercises included here. Everything in this unit, unless it's maybe just a couple of asides, is going to be completely in Euclidean geometry. I think this playlist for sure is very much something that we could do exactly like this is in for high school geometry, except possibly for a couple things at the very end. Okay, all right. So let's start talking about transformations. And the first thing we're going to do is introduce vectors. Okay, so we're going to talk about transformations of a plane, and this will see geometry in action. So instead of thinking of it as just a static set of figures sitting in a plane, we're going to think of it as these figures moving around the plane. Okay, in fact, some geometries we can classify them by how these transformations work. Again, we're going to restrict ourselves to Euclidean plane geometry. Okay, so the first concept we want to introduce is the idea of a vector. So what is a vector? Well, for our purposes right now, vector is a directed line segment. It has a magnitude, the length of the line segment, and a direction given by the angle the vector makes with the horizontal. Notice that this is dependent on an assumed underlying 2D Cartesian coordinate system. Now we can give a vector in two ways. We can specify the magnitude and direction of the angle, say 15 centimeters at 20 degrees. We can also give the vector in component form, which is basically a delta y comma delta x, and we use these little pointy brackets there, like less than and greater thans, to mark off a vector. And that gives us its change, horizontal and vertical change, starting from from the initial point, the starting point or initial point, the tail, and then that goes to the terminal or final point, sometimes called the tip. So it goes from tail to tip. We can start thinking of the tail, start at the tail and slide the point along the vector to the tip. Alternately, we could get there. So here we are. Here's a vector. The blue's a vector like this. This is the vector 3, 9. So we can think of the vector as a starting at this end and sliding along the vector till you get to the end of it right here. Okay, right here at this point. Alternately, we get the same place by going 3 to the right and 9 up. 3 in the positive x direction, 9 in the positive y direction, like that. Okay? Now, unfortunately, this is the same notation we use for array, except for array, we would continue this out to the edge of our window, maybe put the arrow on the end. Like the x-axis here, this is part of a line, and we have the arrow there going on forever, indicating that it goes on forever. This arrow does not mean it goes on forever. This just means it starts at this end and then goes here. So in case of the red one here, going along the x-axis, we start at the origin and we go to the right 2 units. Okay? Now we can also give this same vector by saying how long it is, whatever that length is. We could use the Pythagorean theorem to find that length. And then give the angle that it makes here with the horizontal, the angle between these red and blue vectors. Anytime we look at a graph in this particular unit, we want to make sure we're using a square scale, whether it's with or without axes. We want the coordinates spaced out so that a distance of 1 horizontally is the same physically as a distance 1 vertically, that it only represents that. Sometimes when we're graphing equations, say in college algebra or pre-calculus, something like that, or calculus, we will not use the same scale vertically as we do horizontally. We'll use a consistent scale horizontally, we use a consistent scale vertically, but the two scales might not match. But for this to see what's going on and to understand the geometry of what's going on, we use what's called a square scale so that squares actually look like physical squares. Now, so a vector has magnitude and direction, but the position of the vector is irrelevant. As long as the magnitude and direction are the same, it's the same vector. What does that mean? Well, directions are the same if the vectors are parallel, and the arrow's on the correct end on both of them. And the magnitudes are the same if they have the same length. Okay? So if we have the vector 2, 3, that means we go right 2 and up 3. It doesn't matter where we start. So for example, all of these are the same vector. These are the vector 2, 3, every one of these. Okay, so lots of copies. Now, if you take the one that starts at the origin, it will end at the point 2, 3. But for example, this one that starts at 2, 6, you go to the right 2 and up 3. Where do you end up? Well, you end up at 4, 9, see? Okay, but all of these are the same vector. They're parallel to each other and the same length. And you're going up and to the right, so the arrow's on that end rather than the other end. Okay, so now it's time for your first exercise. Okay, draw the vector 3, 5 on the grid. Okay, just make yourself a grid like this and draw that vector. Okay, and do it at least twice. So we want to draw it once, start at the origin, where the tail is at the origin, do that one, and then draw another one. Okay, and then I would encourage you to try to do this same thing in GeoGebra as well. Okay, in fact, let's take a quick look at doing this in GeoGebra. All right, here's a basic GeoGebra setup. I clicked on here and said show grid, just major grid lines, show the axes. I'm in a basic geometry window here. And I can actually create an actual vector. I could do line segments and stuff, but it actually has a vector option right there. So I can click on vector, start somewhere here, and then end somewhere over here. And now we have a vector. Notice over here in the algebra view, it says we have the vector 2.51. This is an alternative notation for vectors instead of the way we would write it. I'm writing it with like a little less than 2.5 comma 1 greater than kind of symbol, that kind of a thing, little pointed brackets for it. Okay. And what this one says is we're going to the right 2.5 and up 1. And if you look, there's 1, 2.5, and then up 1. The grid spacing is 1/2 each here. So in GeoGebra, you can use this tool here by going to vector, clicking on their initial point and terminal point, and it shows up here as a column vector here. Okay, so we have that. Uh, this is the vector 3, 2. Now we can also do a vector with a vector command, either over here in the algebra view, or if you have the input bar showing at the bottom, you can enter it in there. Vector, we can enter in 2 points. We can enter them by coordinates, like say we can go from the point 1, 1 to another point, that's the initial point, and then a point 4, 3, let's say, for example. And notice it starts at the point 1, 1 and ends at the point 4, 3. And that is the vector 3, 2 to the right 3 and up 2. Okay. Now, if notice, you may have noticed this as we were going along. If you just type vector and you enter in a single point, like say the point 3, negative 2, it will start at the origin and go there. And that gives you the vector 3, negative 2 there, starting at the origin. That is called a position vector. If you're thinking about starting at the origin and going to the point 3, 2, 3, negative 2, that's a position vector. Okay. You can also, of course, have points that you already have. So if we already have, say, a point here and here, let's see what they're named. So that's a point C, and this is the point D. Then I can just go over here and say vector, CD. That will do it. Or of course, I could just use my vector tool. If I already have a couple points like that, like here, I can use my vector tool here to say go from this point to this point. Okay, and so those are vectors, and they can be used later on in other things and further computations. But this shows you these vectors. Now, some of these have control points that are dynamic, so you can move those around. This one, this one, this one. These are not. These look, yeah, it looks like I can control that one a little bit. How about this one? Can I move it? Yeah, I can move it around. This is staying the same vector when I'm moving this around. Okay. This one here, because it's fixed at the origin, this is actually changing the vector. Okay. So we have some different vector commands there in GeoGebra. Okay, so going back to the notes, your first exercise is to draw by hand a vector 3, 5 on this grid, starting at the origin, going the right 3 and up 5, and then also doing it again, starting any other point on the grid that you want. And then here's another exercise. So fill in the blanks with some standard geometric terms to complete the following statement. Two geometric representations of the same vector are line segments which are blank and blank. So how would you describe the comparison with these two line segments here? Okay. And have an arrow on the same end or corresponding end. And they also form a congruent blank with a horizontal ray pointing to the right. So if you put a horizontal ray, what can you say that they form there that's congruent from each one of these? So see if you can come up with it. These are real standard words that we use in geometry all the time. Once again, here's just some in words what you already saw about how to create vectors in GeoGebra. And then the exercise 3 is in GeoGebra, create a vector controlled by two sliders. Are slider input boxes. Slider / input box combos. Okay, and hopefully we've seen that how to make a slider before, and you can do that. Okay, so that's a basic introduction to creating vectors.